speaking of recording, something went really, really wrong last class. If anyone has gone to the recording from last Monday's class, it's only like 18 seconds long. I have no idea why, and that's what worries me. Because I feel like I remember starting recording at the beginning of class, like always, and ending at the end of class, like always. I could be misremembering that, or maybe confused with my other class that happens right before it, whose recording was fine. But something, and actually, I need to, I guess what I should do is watch it, those 18 seconds, and see, like, is that from the beginning of class, in the class? But can anyone corroborate that? Like, did I start recording at the beginning? Again, you might not really see it on the screen when I do. Because sometimes it'll say, this meeting is being recorded, but yeah.
I don't know if this was the same day, it's for real, but there was one day I was sitting in here. Was it the last one, the one you were late for?
Possibly.
Or was it I'm asking because there was one day I was sitting in here and the camera was doing all kinds of weird stuff before class, like it was zooming in, zooming out, going everywhere. So I don't know if maybe it was just a weird day.
I don't know. Yeah, so, I mean, this has only happened as far as I know that one time.
Mm-hmm.
Yeah, actually, the only reason I found out about it was Dr. Tian had mentioned that when she does an IBM class like these and records, that there's no audio. And I never watch these videos. I hate watching myself, or even watching or listening to myself talk. I'll check. And yeah, I do get audio. But, and I would hope that if any of you did go watch videos, like if you couldn't attend class, and found there was no audio, that you tell me. So, never know. There's a lot of problems that students don't bring to my attention. So yeah, the audio was fine, but I had this non-existent recording.
Or you can always go and watch your 2 years ago class or whatever you called it.
That's right.
Mm-hmm.
YouTube.
Yeah.
What?
YouTube.
Yeah, okay.
Yeah. I know every one that I've watched of yours so far, everything's been fine. The audio is there, it was synced with the video, and
Okay.
there's no problem.
Yeah.
And they've all been more than 18 seconds, so.
Yeah. It felt bad because in your case, you were away. And I thought, oh God, he was not going to be able to, but okay. So you have something to fall back on. Okay, yeah, it's not, I'm checking, like, okay, so it shows on my screen recording and how long it's been recording for. So, yeah, because I remembered that when class ended, when I went to stop recording, it had recorded about an hour or so. And, I don't know. Let's just hope it doesn't happen again. Okay. Let's see, now there's supposed to be some, I think there's some announcement I'm supposed to make. Yes, there is. Okay. All right. So for homework, I need to make sure which assignment this is for. For homework 7, there's a one-step method, what I was just covering, like Euler's method, Fourier methods, etc. There are certain whole problems where you write a MATLAB function that implements one of these methods. Like starting with Euler's method, and there's number 1 for RK4, etc. I've updated this in Canvas, but I need to make sure I do it on the other side too. Let me check. Okay. I need to fix something on the side real quick. I'm going to forget otherwise. Okay, under homework 7. Okay, I just posted hints for that. And just I need to make sure that this is something that I actually did as opposed to something I said fun was doing and forgot. Okay. Wow. Go to conference for a week and I get everything. Yep, it's not on Canvas either. Wow. I blew this all the way around. Oh wait, I'm in the wrong class. Okay. Oh, good. Everything is there. This is gonna be fun. Okay, so now everything is set on both versions of the site, and then I can tell you what I am referring to. Okay, so for all the homework assignments except for the first one, I have posted a PDF that hints on each assignment, and that's true for homework 7 as well. But for this homework, I have something else. So there's a MATLAB file that I put out there called timestep.m. And there's not any actual code in it, it's comments. So the idea is, when you go to the first problem, which you have to implement a time-stepping method, which is a forward Euler, I suggest looking at this file, timestep.m, that gives some pointers on how to write a MATLAB function that does time-stepping. So use that as your starting point. And then if you have any difficulty, then that's when you can let me know. Because once you do that for Euler's method, then to change it for other methods like 4-4 it's not hard to do, because of a general framework, like a loop, for instance, that carries out the time steps, that part is going to stay the same. There's a certain steps in how you compute yn plus 1 from yn. That's what's going to change. So I want to give you at least something to go on. So be sure to look at that first. All right. Now, that's about one-step methods. But today we're going to talk about a very different kind of time-stepping method known as a multi-step method. All right. So, what we've seen in higher order one-step methods, like 4-4 you're solving the ODE y prime equals f of ty, and to achieve higher order accuracy, you end up evaluating f several times. So 4-4 evaluates 4 times. There are certain second order methods where f is evaluated twice at different values of t and y. And like I said, the order of accuracy is not always equal to the number of evaluations of f, but there is some correlation between them. And that's a lot of work. So to get a higher order of accuracy you want, the more work you have to do during each time step. That partially offsets the benefit of getting more accuracy. Fortunately, it is not necessary to do this much work just because you want high order accuracy. And that's what multi-step methods are for. So we'll find a way to still get higher order accuracy for the same amount of work per time step in terms of evaluations of the time derivative f. So here we have our framework for a multi-step method. And this is one of those things where you'll find this written in different ways in different books, which is kind of aggravating because I get used to teaching about it a certain way, and then if I'm using a different textbook, they really write it differently, and I have to adapt everything to that notation, which I guess is one good reason for writing your own textbook. Problem solved. Okay, so to decipher this for you, what we have on the left side is a linear combination of solution values. So for instance, we have, if I equals 0, we have yn plus 1. And then for I equals 1, we have yn. And going backwards in time. the yn minus 1, yn minus 2, etc. So there are more y values involved than what we've seen in a one-step method. Because remember, a one-step method only uses information from time tn to time tn plus 1 to figure out yn plus 1. Multistep methods are allowed to go further back in time, use older information about the solution. And then on the right side, we have a linear combination of different coefficients, these betas. You have your time step h. And we have f evaluated at certain time values. Notice the indices are the same as what we have over here. And then corresponding y values. One thing that's worth pointing out is, notice the indices for the t values and the y values are the same when you plug into f. Unlike Runge-Kutta methods, where you have all these different expressions for times and t values and y values that you plug into f, all different kinds of expressions to get a certain order of accuracy. None of that here is all uniform. These t values matching y values. Now, the value m here is the number of steps. So if this was a one-step method, m would equal 1. But we're interested in methods for m greater than 1, which is what makes it a true multi-step method. Also, because the t values and y values have the same indices, we can abbreviate this. So this is a notation that I'll use going forward. F sub k is equal to f at tk yk. So that makes the method, the way it's written, a little less cluttered. Okay. So, suppose that we've already computed y up to a certain point, yn minus 3, n minus 2, and minus 1 yn. Therefore, these f values we will also have already computed. So, if I want to compute yn plus 1, I'm going to need to evaluate f at tn plus 1, yn plus 1. Or if this were an explicit method, I've just computed yn, I need to plug it into f and get f of tn yn. So, other values of f, I've already computed. That happened during earlier time steps. So, it's only absolutely necessary to get one new evaluation of f every time step. Unlike higher order Runge-Kutta methods, where you have multiple evaluations of f every time step, and the information that you carry out for evaluations of f during a time step cannot be reused in the next time step. Here we have a lot of information to reuse. Now, so that's one nice thing is that means in terms of work per time step, it's more efficient than one-step methods. But here's the problem. You can't use a one-step method from the get-go. For example, suppose you have say a 3-step method. That means you need yn minus 1 and yn minus 2. But when you start, you have y0. And then you're going to use that to compute y1. Well, that 3-step method is going to need y sub minus 1 and y sub minus 2. You don't have that. You have no possibility of getting that. Forget it. So what that means is you have to generate what are called starting values using a one-step method. So multi-step methods cannot replace one-step methods in their entirety. They do need a one-step method's help to get the ball rolling. So So for example, for that 3-step method that I've been using as an example, I need to take 2 steps using a 1-step method. So I need to compute y1 and y2. Then I can use my multi-step method to compute y3 using y2, y1, y0. And then keep using the multi-step method from there. Very important, you need to make sure that the order of accuracy of your helper 1-step method is greater than or equal to the order of accuracy of your multi-step method. Because if you taint your solution with higher order error, like first order error when you want third order accuracy, then that is going to make your whole solution first order accurate. So make sure that you choose your helper 1-step method wisely. Now, we've seen both implicit and explicit 1-step methods. Same is true of multi-step methods. Very easy to tell if a 1-step method is implicit or explicit. Is there a beta 0 term? So I goes from 0 to m, but some of these coefficients are allowed to be 0. So if beta 0 is 0, the method is explicit, otherwise implicit. Because beta 0 is multiplying f evaluated at time tn plus 1 and yn plus 1. So if you have a beta non-zero beta naught term, you have y plus 1 on both sides of the equation, you have to solve for it. That's what makes the method implicit. And as with 1-step methods, if your method is implicit, you need to use some sort of iteration. Newton's method, CK method, or even fixed point iteration to solve for yn plus 1. So in the case of like Newton's method or CK method, you're solving an equation f of y equals 0. So what I've written out here, this is the multi-step method, same multi-step method, but I've moved everything over to one side and set it equal to 0. So in this case, your function is f of y. Your unknown is yn plus 1. So here's our unknown here. Oh, whoops, this is wrong. This should be f of tn plus 1. Y. Okay. And now I have to check. Did I make that same mistake in the textbook? If I did, I'm going to be so pissed. I have a long and growing list of mistakes that I'd like to fix in a later edition if my publisher would let me. Oh, it is correct in the book. Okay. Not sure what I was thinking when I was making these notes, but okay. So we could use one of the root finding method to find a root of this function, and so the root of this would be yn plus 1. All right, are there any questions up to this point about multi-step methods? use Newton's method to find a root of this. Well, Newton's method, as you know, requires a derivative. So that means I would need the partial derivative of f with respect to y. For Newton's method to be well defined. But keep in mind, other y values, yn minus 1, etc., and also these older f values, those are considered constants. Those are y values that have already been computed. So that simplifies matters. Your only unknown is yn plus 1. Everything else treated as a constant. Okay. Now I can get into certain categories of specific multi-step methods. So there are certain families of multi-step methods that are often used. Now, not all Adams method fall into these, not all multi-step method falls into these families, but these are the best known. First kind of multi-step method is called Adams method, invented by some dude named Adams. So what you do is you take the ODE and you integrate both sides of it from time tn to time tn plus 1. And you get this. This is exact. The idea behind Adams method is to approximate this integral by interpolating this integrand, f of s, y of s, at certain time values. Tn plus 1, tn, also earlier time values, tn minus 1, tn minus 2, etc. To take advantage of what is already known about the solution. So we use Lagrange interpolation to interpolate f at these times. So for an explicit method, you use time tn minus 1, and you keep going back. However many steps your method has, that's how many time values you use. So for instance, if this was a 3-step method, you would use 3 time values, tn minus 1, tn minus 2. For an explicit method. If you want an implicit Adams method, you would also include tn plus 1 as one of your interpolation points. So a 3-step method would use 4 values altogether, tn plus 1, tn minus 1, tn minus 2. Now, multi-step methods in general have 2 types of coefficients, the alphas and betas. For an Adams method, the alphas are always the same. You always have alpha 0 is 1, alpha 1 is minus 1, and no other alphas. So the only y values appearing on the left side of your method are yn plus 1 and yn. If the Adams method is explicit, again, that's when beta not is 0, it's called Adams-Bashforth method. Otherwise, the implicit is for Adams-Moulton methods. What's interesting is both types of methods were actually invented by Adams. Bashforth was a collaborator of Adams, but in a situation where you have a mathematician collaborating with someone from another discipline, and some ODEs came up, and Adams designed a method to help Bashforth with his application. How Moulton came into the picture was he recognized that because Adams had invented both explicit and implicit multi-step methods of this type. Moulton recognized that an explicit and implicit method could be used together in what's called a predictor-corrector method. And I'm going to talk about that a little later. So that was Moulton's limited role. Speaking of naming methods, so for my own research, I've built what are called Preload Subspace Spectral methods, which are time-stepping methods that are closer in nature to one-step methods, and that they only use information on the interval Tn and Tn plus 1. But very different from the kind of one-step methods that I've covered here. And for years, I've wanted to have a multi-step version of them, and that is what our own Billy Rester is doing for her dissertation. And I was thinking, like, well, it'd be kind of cool. They're actually very close. They're similar in nature to Adams methods. So maybe the explicit versions can be called like an Adams-Bashforth-Rester method, or an Adams method. I don't know if she'll go for that, but it's something I think would be cool to see happen. Okay, now, so I'm going to show you how an Adams method can be derived. And my example will be an explicit or Adams-Bashforth method, so for a case of m equals 3. So for a 3-step method, you need the values of f at time tn, tn minus 1, and tn minus 2. So the general form of your 3-step explicit Adams method is right here. So we have these 3 betas to figure out. If this were an implicit or Adams Moulton method, I would have an additional term in here that would be beta 0 fn plus 1. So you have an additional term in here. But once I show you the explicit case, you'd see how to be able to adapt this to derive any Adams method. Now, I want to interpolate f at these 3 points, these 3 times. Since we have 3 of them, that means our interpolated polynomial is a quadratic, so a degree 1 less than how many points you have. So, if I define P2 of t to be an interpolating polynomial that fits this function at these 3 times, I can express that interpolant in Lagrange form, which is more convenient for what we're trying to do here. So it's this linear combination of the f values that I have in my method. So now my integral that came from the integral form of the ODE, so this is exact, is approximated by the integral over the same time interval of my interpolant. But then what I do is I make a change of variable for convenience. That's a U substitution. So this U substitution maps the interval Tn of Tn plus 1 into the interval 0 to 1, where this endpoint corresponds to U equals 1, the other endpoint corresponds to U equals 0. So that makes the du negative. And the reason why I do that is my interpolation points, Tn, Tn minus 1, Tn minus 2, correspond to U equal 1, 2, 3. So this change variable maps the times in which you want to interpolate f into the positive integers from 1 to m, whatever m is. So now, this integral, I use Lagrange form, interpolating f at u equals 1, 2, and 3. So here's my Lagrange form here. And now I fill in the actual Lagrange polynomials. They're quadratic. Then I use the linearity of the integral. I could break this up into 3 integrals. In each integral, the f value is a constant, so I pull it out. So now, I have f times this integral. Oh, I forgot to pull this one. Out of the integral. Yes, I just made sure that in the book I did. So now the integrals that remain I can just evaluate those. And those are my betas. And these are values I get. Notice that they sum to 1. So that's true in general. So there's my method. Y plus 1 equals yn plus h times this summation of beta values times f values. And I'm done. So in general, the betas are the integrals from 0 to 1 of Lagrange polynomials for the points 1, 2, 3 up to m for an explicit method, and then 0, 1, 2 up to m for an implicit method. The questions about how this Adams method was derived. So in general, Adams Bashforth method, it's m steps, the error is h to the m. Same value of m step Adams Multi method, or h to the m plus 1. So the order of accuracy is 1 degree higher because you have one additional interpolation point, 0, corresponding to tm plus 1. So the higher degree interpolant, for same value of m, leads to the higher order of accuracy. Now, as I mentioned with implicit method, whether it's one step or multi-step, if you're just going to use an implicit method by itself, you have to carry out some kind of iteration to solve for yn plus 1. But what most recognized is if you instead use an explicit and implicit method together, so you first compute yn plus 1 using the explicit method, and then you use that value of yn plus 1 to plug into f for the implicit method, then you still have a higher order accurate method. It's almost like, one way to think of it is, because you're computing a value of yn plus 1, a good approximation of it, you can think of it as using a really, really good initial guess for the implicit method, and the initial guess is so good that you just carry out one iteration and call it good. So using the two together gives you what is called a predictor-corrector method. So here's the procedure for using two methods. The explicit method is called the predictor. The implicit method paired with it is called the corrector. And it's abbreviated PECE, predict, evaluate, correct, evaluate. So what do? Go ahead and use the explicit method, the predictor, and that gives you an approximation of yn plus 1. And I'll call yn plus 1 tilde. Then you plug that into f at time tn plus 1. And we'll call that fn plus 1 tilde. Then, where the implicit method calls for using fn plus 1, you substitute fn plus 1 tilde. And now, it's like you're using the implicit method kind of like an explicit method. There's no iteration here. It's just plug and chug, like you would for an explicit method. You're going to get a new yn plus 1 value, now we call yn plus 1 with no tilde. Now, normally your f values you would use for the next iteration, next time step. But this one's out of date, because now we have a new and supposedly better value of yn plus 1. So that's where the second evaluation comes in. We plug this into F. Notice the time value is the same. And that is what you will use, which now will be the Fn in the next time step. Now, what you could do if you wanted is continue iterating with the implicit method, knowing in your head is really good initial guess, but you don't have to get higher order accuracy. Here's an example. So I have a two-step Adams-Bashforth method as my predictor, and I have a two-step Adams-Moulton method as my corrector. Notice both methods go back to time Tn minus 1, but this has one additional term because it uses time Tn plus 1, whereas the explicit method doesn't. So I just go ahead and apply the explicit method. It gives me yn plus 1 tilde, plug that into F, and it gives me Fn plus 1 tilde. Then this Fn plus 1 value is used here. Notice this Fn plus 1 tilde. I carry out the implicit method, and I get yn plus 1. Then that gets plugged into F, and this is used next time where the method calls for Fn. Questions about how predictor corrector method works? I actually have a theorem about the accuracy of a predictor corrector method, but it's actually introduced in the next section on convergence analysis. I'm going to hold off on covering that for the time being. Okay. All right. So that's one family of multistep methods, Adams methods. Here's another called backward differentiation formulas. Now, backward differentiation formulas are always implicit. In fact, there's only one non-zero beta value, it's beta 0, which is set equal to 1. So that is what makes the method implicit. And instead of computing betas to approximate an integral like in an Adams method, we're computing alphas to approximate a derivative. So it's the opposite in that sense. So here's a general form of a BDF. So a very simple right-hand side, then we have this linear combination of y values. The alphas come from taking derivatives of the derivatives of Lagrange polynomials. So if you may remember from last semester, for numerical differentiation rules, we use, you can get the coefficients in a numerical differentiation scheme by taking derivatives of Lagrange polynomials at the point at which you want to approximate the derivative. And that's exactly what's done here. So the order of accuracy, the m-step method is mth order accurate. But you only go so high in the order of accuracy. Once you get order greater than 6, BDFs are unstable. And I'll have more to say about stability in the next section. I'll just make this one point that We have that the ceiling to contend with. BDFs are used in certain MATLAB ODE solvers, like there's stiff solvers, like ODE 15S is a particularly effective one. So solvers like that make use of certain BDF formulas of varying orders of accuracy. And there are certain multi-step methods that are neither atoms nor BDF. But in mathematical software packages, usually it's one of these that are used. And often as preferred over one-step methods, just because they're generally more efficient. So, questions about multi-step methods? Or on homework problems? Or has any homework been happening? When I was away last week to the conference, I come back, like, okay, how much grade are you going to catch up on? Like, oh, wow, not much.
You're welcome.
Yeah.
Until you're not.
Yeah, and then this is across 2 classes, so yeah, there's only like 7 assignments in my pile. I think, but that's mostly from every class. So, well, it makes for a fun end of the semester. If you haven't already, I recommend you start thinking about what you want to do as far as the final is concerned. There's coding option. Now we haven't got to that material yet, but the coding option is only on boundary value problems, which is what we're coming to at the end, or taking an oral final that is comprehensive. So, I still have plenty of time to think about it, but what you might already know.
You can put me down for oral.
Yeah, that's what I want to know. How exactly does the oral work? Like, how long would it go, and what kind of questions are we expecting?
Okay.
Should we expect?
I would say roughly like 45 minutes-ish. Preferably done in person, like in my office, so that it makes it feasible to like for a student to write a board. And the questions I would ask are kind of like what you see in the quiz. And I got here writing that on the board.
No long questions, isn't it?
No, yeah. Like testing conceptual knowledge, that sort of thing. But what I might have someone do is work through something to illustrate whatever concept I want to ask about. So.
When you say work through something, like, is it kind of like I don't know, like you would would it be something kind of different, a little modified or different than what we've done, and you're like stepping us through it, or is it more just do this?
That it is a possibility.
Yeah, okay. No, I'm just curious. I've only had one oral exam before, and it was
So, for example, if
a little
you're
more
asking-
conversational than I thought, but I don't know.
Well, yeah, that's likely to happen.
Okay.
It's easier.
Okay. Like, if, for example, we have the LU decomposition problem in the very first test. So if you just say like, hey, take this particular system of equation and solve for it.
Okay. Wait, let's see if I get something in the chat here. Oh, okay, one question I got was, will we be responding purely off the top of our head, or will we be able to refer to the text? Okay. I generally prefer off the top of your head. In certain cases, like for occasional detail, I can see referring to the text. But it's not something I'd want it to be done all the time. Because the idea is to have some knowledge off the top of your head. Okay, and you were asking about,
Solving, problem solving.
like for example, I remember there was a homework problem where you were given a specific matrix and do the decomposition. I think it was like a 4x4 or something. I'm not going to do that. However, okay, here's an example. And of course I won't be able to ask a specific question, but I think it's illustrative. Like Yelly factorization exists if and only if all the principal minors are non-zero. So all the leading principal submatrices have to have a non-zero determinant. So for instance, I might make up a matrix for which that's going to fail, and you explain to me how you know it's going to fail without having necessarily grind through it. Because you can see, like, oh, that one entry is 0. So it's going to fail for that reason alone. Or the upper left 2x2 block is clearly a singular matrix. You know, that kind of thing. So I might use like specific examples to support my question about a concept. But not for the purpose of working through something tedious. You know, it just occurred to me that, yeah, for a couple of you, I said I prefer in person. Yeah, for a couple of you, that is not feasible because you're remote. And that's fine, we can do remote circumstances, but if you're here in Hattiesburg,
What time or what date are we expecting the finals?
well, that's something we work out.
Okay.
I mean, during finals week is easier, scheduling wise, or it could be a week before if you want to get on a little bit. Oh, so you don't have a lot of questions about this anymore. Okay. See if I have a recording. Supposedly I do. Hopefully I still have one. But I go to upload.